this morning we will be looking at starting the next unit, and the next unit is on a mathematical concept called the quadratic. And you may remember quadratics for a little bit from grade 10. We do cover it again and go into a little bit more detail in grade 11. Quadratics are relations, as you can see, that can be used to model many different real-world scenarios. I've shown a few pictures here. Oftentimes, quadratics are used to model projectile motion, so any kind of object being kicked will, like this one here, okay. The St. Louis Arch, which is this one here, a lot of people mistakenly think it's a parabola, but it's actually a shape called a catenary. Very, very similar to a parabola. Catenary is actually the shape that a chain hanging between two posts will follow. But that's, I mean, you can still use a parabola to approximate the shape of this kind of thing, but it isn't technically a parabola. And then we have also arches, like this one, and certain fountains of water will also follow parabolic shapes when the water is being shot through them. So there are many different places where parabolas will actually be used to model scenarios. Another one that's not quite as visual is revenue. If you're selling items, you can use parabola to represent revenue. So there are many, many different situations. So quadratics and parabolas are related because the word quadratic is related to the equation, and the word parabola is related to the shape of the object. So oftentimes, even myself will interchange the word quadratic and parabola because they're so closely related, representing two different things, but I'll often use them for the same thing. So I'll try not to, but it is difficult not to. Okay, so let's look at an example of where the idea of parabolas might come into play. So several farmers have square fields of different sizes. They want to know how much fertilizer to buy, given that 6 bags of fertilizer cover 1 hectare. The unit for hectare is HA. Note that 1 hectare is 10,000 square meters. So what we're going to do here is we're going to start with different sizes of farms, and I'm actually just using your textbook for this. The example in your textbook, here, let me just find the page. It's on page 168. So we're going to start with a side length of 100. We're going to move up to a side length of 200, and then a side length of 300, and then 4, 5, and 600. I'm not going to do those as pictures. I actually did try to make sure that these were exactly double the size of the original. So if you look here, if I move this square into this square, and you kind of mark off where the center of the square is, if I move this down, it's pretty much exactly twice the size, and I made sure that this one was pretty much exactly 3 times the size. Okay, so it's pretty representative of exactly what it would look like. And you can see that the area dramatically increases as you increase in size here. So we need to calculate how many hectares does each one of these fields cover, okay? So there's a couple of ways that we can do this. So we know that this is 100 by 100. Now, the area of a square is a formula based on the area of a rectangle, which is length times width, which often gets replaced as side times side. And I'm going to use this fancy S here to represent side, so it doesn't look like a 5, okay? So S squared, which if you prefer, we can just call length squared. It might be easier. I'm still going to use a fancy L, though, to make sure it doesn't look like a 1. So either way is fine, all right? Basically, what I'm trying to get to, though, is that the number is being squared. So what is 100 squared? Well, 100 squared, the quick way of doing this without a calculator is there's 2 zeros in 100. And as soon as you multiply things with a bunch of zeros at the end, basically you're just adding up how many zeros there would be. So it's 100 times 100, which would mean 4 zeros. 4 zeros is 10,000. So this is actually 1 hectare. Okay. Now if we go to the 200 length side for the square field, we would now be doing 200 times 200. Which is 200 squared. Okay. Now what is 200 squared? Now a lot of students and people, in fact, will mistakenly say that this would be 2 hectares. But it isn't. And you can see it if you take this square, I'm just going to physically do it here, and move it back into this shape. How many of those squares make up the bigger one? It isn't just 2. If we divide this down the middle this way, and we divide this down the middle this way, there's actually 4 of those squares inside of this shape. So 200 squared is actually 40,000 square meters, which would be 4 hectares. So I'll just leave some room in here to write that down. Okay, so doubling the side length has changed the area to 4 times what it was before. Okay, so what would happen if the side length was 300? Well, 300 times 300 is 300 squared, and I'm hoping you can see that that would be 90,000 square meters. And 90,000 square meters is 9 hectares. Okay, and again, if you broke this down into 3 by 3 squares of the original size, you could see that as well. So we're not just doubling, we're not just tripling, there's some other pattern happening here. So let's take a look at that pattern in a table. So I'm just going to quickly make a table here. Okay, so we'll call this side length. We'll just call it the side length. And this is in meters. And then for this one, we'll do the area of the farm in hectares. And then this one we'll do bags of fertilizer. Okay, and I can just make this a little bit bigger here. All right, so we started with 100, we went to 200, and 300, and 400, and 500, and 600. So the first one was, and I'm going to try something here, I think I can write in here 1, and then this one was 4, and then this one was 9, and this one would be 16. So what I'm doing to figure out the next one is I'm just using the same pattern. If I multiply 2 by 2, I get 4, right? 200 times 200 was 40,000, but then I have to divide by 10,000. So if I just multiply the first number by 2, by itself, sorry, my mistake. So 2 times 2, 3 times 3, 4 times 4, 5 times 5 would give me 25. and then 6 times 6 would give me 36. So how many bags of fertilizer? We need, so 6 bags of fertilizer cover 1 hectare. So this would be 1 times 6, which equals 6. And this would be 4 times 6, which equals 24. And then 9 times 6. And then 16 times 6. And then 25 times 6. And then 36 times 6. So I'm just going to use my calculator off to the side here and calculate what all those values are. So that is that table filled in. So the next question that they're asking us to do is to draw a graph comparing the bags of fertilizer needed to the area of the fields. So they want us to draw a graph of this number versus this number. Okay. Now to do that electronically, to make our lives a little bit easier, we're going to use Desmos. And Desmos is either an app or a web page that you can get to. So I'm going to switch over to that right now. And I'm going to show you how to use Desmos to graph information like this. Okay. So what we want to do is we want to make a table of values. So I'm going to add an item. Once I get to Desmos's website, I'm going to add an item, and I'm going to add a table. Okay. So we need to do bags of fertilizer versus the area of the farm. So bags of fertilizer are going to be our y-axis, and area of the farm is going to be our x-axis. So I'm just going to type in each number here. 1, 4, 9, 16, 25, and 36. And pressing enter between each number will just go down to the next line. So then we have 6, 24, 54, 96, 150, and 216. Now the problem is we only see one dot here because that's the first dot, 1, 6. The 424 is way off the graph. So the problem here is that we have a scale that isn't correct. Now we can just zoom out. You can click and drag to move the graph over, and we can zoom out to start seeing our points. But what I'd rather do is set up what we call the domain and range of the graph. So if you press on the wrench icon, you can get to this table here, the settings table, and you can see that our x-axis values go from -16 to 63, while our x-axis values go from 1 to 36. So I'm actually going to just change the lower end of the x value here, and you can do the same thing as well, to 0. And I'm going to change the upper end. I always like to go a little bit lower and a little bit higher than the numbers that are there so we can see all the points. So I'm going to go to 40. Now for the y-axis, again, I'm going to start at 0. 0, 0 is always a nice point to start at if we can. But it goes all the way up to 216. So I'm going to go all the way up to 230. Okay. Now, you can see here that this graph is actually a straight line, right? So the relationship between the number of bags of fertilizer to the hectares is actually not a quadratic. it's a linear relationship, which is interesting. But that should make sense because if you remember how we calculated it, we just took our numbers of bags of fertilizer, multiplied it times the number of hectares. So we were always multiplying by 6. Okay? So that's the first graph. Now, the next one they ask us to do in the textbook is draw a graph comparing the bags of fertilizer needed to the side length of the fields instead. Okay? So let's just go back quickly to the table. So they want us now to do a graph of the bags of fertilizer with respect to the side length. So the bags of fertilizer is going to be our y-axis, and the side length is going to be our x-axis. So the only thing we need to change in our Desmos graph here are these numbers are going to be 100 and then 200 and 300. Oh, I'm making a mistake, sorry. I'm going to have to click over top of them to change them. So once again, we can't see our table because the scale is way off. So we're going to change our x-axis starting point to be, let's put it back to 0. And we're going to go all the way up to 650. And we're going to change our x-axis values to start at 0 and go all the way up to 216. So let's go up to 230 again. And let's look at those points. Now, I'm going to zoom out just a bit here. Those points actually do form a curve. They don't go up as a linear relationship. You can see that if you aimed at these 2 points and continued going, you wouldn't connect to all of them. So same scenario, 2 different graphs. Right? So this one gives a parabolic relationship, and the other one gives a linear relationship. So as you can see, different scenarios can give different relationships depending on how you graph them. Okay. Now, let's move on to the next slide. So what are some of the patterns that you have to be looking for in quadratics? Well, there's a pattern in the formula, there's a pattern in the table, and then there's a pattern in the graph. So what's special about the formula of a quadratic? We've seen that y equals mx plus b in grade 9 is the equation of a straight line. Now this might have been shown to you in a slightly different way in grade 9, but in grade 10 you usually start using the mx plus b format. Okay, but that is the equation of a straight line. We're doing a parabola. The simplest parabola is y is equal to x squared. Now what makes a formula give, so I just used the word parabola instead of quadratic. This makes the equation a quadratic. Okay, the power of 2, if it's the only power in the equation next to an x, gives us a quadratic. So as long as you have a power of 2, so if you have, for example, y is equal to 3x minus 4x squared, as soon as you see a power of 2, it doesn't matter, as long as the other letters are just x's, as long as the highest power is a power of 2, you're going to have a quadratic. So you could have y is equal to 4x squared minus 3x plus 5. That would be the equation of a quadratic because, again, the power of 2. Okay? But the simplest equation, and I'm just going to erase these two, is y is equal to x squared. Now, from the equation, we can generate the table of values. And all we're going to do is we're going to substitute x into the equation and find out what the corresponding y is. So y is equal to x squared. So if x is equal to negative 3, what would we get as our y value? Well, if we sub in negative 3 into here, we get 9. If we sub in negative 2 into there, we get 4. And now we can do that just in the table now. What is negative 1 squared? Negative 1 squared is 1. What is 0 squared? 0 squared is 0. What is 1 squared? It's 1. Let me fix that 0. What is 2 squared? It's 4. What is 3 squared? Is 9. Now you can see some very interesting things happening here. Okay, going backwards from 0 into the negative numbers, we get the exact same values for y if we go forward from 0 into the positive numbers for our x values. Okay, so the y values are symmetrical around the 0. All right, so if I went to 4, I'd get 16. If I went to negative 4, I would get 16. Okay, so I know that they're going to be the exact same numbers around this 0 point. Now there's another pattern that comes up, and that's from our first differences. Okay, so we're going to do our what we call finite differences. Complicated word to just mean subtract upwards. Okay, so what's 9 minus 4? 9 minus 4 is 5. Okay, now I'm not going to show the whole subtraction because I'm going to run out of room if I do that. So I'm just going to go back to just a 5. What's 4 minus 1? 4 minus 1 is 3. What's 1 minus 0? That's 1. What's 0 minus 1? That's negative 1. What's 1 minus 4? That's negative 3. And what's 4 minus 9? That's negative 5. So we still have an interesting pattern going on here. But the problem is when you're doing differences, you're trying to figure out when do they become the same. Okay? And if your first differences are the same number all the way up that column, then we know that this relationship would actually be linear. They're not the same, so we're going to keep going. What is 5 minus 3? It's 2. What is 3 minus 1? It's 2. What is 1 minus negative 1? Now when you do 1 minus negative 1, that becomes a negative scenario, which becomes a plus. 1 plus 1. That is also 2. Negative 1 minus negative 3 is negative 1 plus 3, which is also 2. And I'm sure you can see the pattern here. All the way up is 2. Okay? Now it's just a coincidence that this matches the power of 2. So don't think it'll always be a 2 here. But what is important is they're all the same. And those are our second differences. Okay? So we call these finite differences because you have to keep going until you get a constant number. And in future years of mathematics, you might see a cubic relationship instead of a power of 2. You'd have a power of 3 here. In a cubic relationship, you'd have to go 3 times before you would get the what we call the common difference. Okay? So if your second differences are the same, we know that that's quadratic. So why would that be important? Well, if I go back to the previous slide here, if we check to see where our second differences are the same, in which row, well, if you look over here, 600 minus 500 is 100, 500 minus 400 is 100. That means all of our first differences would be the same. But what would happen if we did these ones? Okay, so 36 minus 25 is 9. 25 minus 16 is 4 plus 5. Wait a second. 5 plus 6, that's not 9. Sorry. That's 11. This one's 9. 16 minus 9 is 7. 9 minus 4 is 5. 4 minus 1 is 3. Okay, those are clearly not the same. However, if we do our second differences, we also get 2. Okay? Which is making me start to wonder that maybe I made a mistake earlier and said it's just a coincidence that it matches the power. But I think it's still just a coincidence. Okay? But anyway, what would happen if we did these ones? So you can check to see whether it's going to be quadratic before you actually graph it just by doing your first and second differences. And that's the reason why I'm showing you how to do first and second differences. If I give you a table of values and I ask you what relationship is that table of values, you can just check with your first and second differences without even having to graph it, even though Desmos does things pretty quick. So what would the graph of this table look like? Now when we graph it, we're just graphing the x's and y's. Okay. Now I want you to try to visualize this in your head. The y's are how high up the graph you are, and the x's are the horizontal distance, right? So I'm just going to quickly put a couple of axes here. And this is just being done by hand, so I'll try to do it as accurately as I can. So I'm going to put some tick marks to represent our x-axis values, trying to keep them 1, 2, 3, 1, 2, 3. So this is -3, this is +3, this is 0. And now I'm going to put some tick marks going up. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll go all the way up to 10. And 1, 2, 3, 4, 5. So this is 5. So you don't have to label every point. Okay. Let's plot these numbers. So I'm going to go -3, 9. So -3 is here. I'm going to go all the way up to 9. And then -2 is 4. Then -1 is 1. 0 is 0. 1 is 1. 2 is 4. 3 is 9. Now you're starting to understand why I was talking about symmetry when I was doing the table. Okay? It doesn't matter how far over to the left or how far over to the right you go, you're always going the same height at that distance on either side. And the heights are going to form, this is very difficult to do on my tablet, so I'm not even going to try, folks. But if you draw a curve through those points, you're going to get your parabolic shape. Okay? So let's talk about some of the words that you need to know here. And this is a refresher from grade 10. This point down here has a special name on a parabola. It's called the vertex. Okay, it's where both sides connect at a peak, or in this case a valley. Okay, so that is called the vertex of the parabola. You can draw a line down the center. Let me use a straight line here. you can draw a line down the center of a parabola, and that line is called the axis of symmetry. Which is another word that you need to know for parabolas. Okay, now I drew that a little bit thick, so I'm just going to move it out of the way. I'm not sure if there's a way that I can make that thinner. No, there isn't. Oh yes, there is right here. Thickness. Okay, perfect. So the axis of symmetry is the line going straight down the middle of the parabola, and the parabola is symmetrical along either one of those sides. So that is going to be it for today's lesson. There's going to be some homework questions given to you. If you're asked to graph something, please use Desmos to do it, as it's much quicker than doing it by hand. And I can't necessarily assume that you have graph paper at home. And we will talk to you soon. Have a great day.